Okay, today we're going to look at volume by known cross sections. And in this lesson, we will use calculus to find volumes of three-dimensional shapes where the cross sections are geometric shapes like squares, triangles, semicircles, rectangles, and such. Finding the formula for the area of the cross section is the tricky part. But once we figure that out, then just integrate like you've been doing. In general, if the cross sections are perpendicular to the x-axis, solve the equations for y, and if the cross sections are perpendicular to the y-axis, we solve the equations for x. So let's take a look at a simple example. Let's take a look at a loaf of bread. Now, when we slice the loaf of bread, notice that the slices are identical. They may be different sizes, but they're all identical. And if we were to get the volume of this loaf of bread, I don't know how many slices there are. Let's say there are 20 slices in this loaf of bread. They all look identical, and they look something like this. Let me just adjust this a little bit so you could see it. So they look something like this. We call this outer piece the cross section. The crust of the bread is going to be the width of the cross section. So depending on how wide the crust is, we'll call that delta x. So to approximate the volume of this loaf of bread, we would find the volumes of the cross sections and add them up. So we would have 20 slices. We'd get the volume of these 20 slices. Hopefully the slices are evenly cut. And we add up the areas of the cross sections plus times the width. All right, where would we place this loaf of bread on the XY plane? Well, if I draw the XY plane here, I'll try to draw it as best I can. It would make sense that the base of the loaf of bread, which is a rectangle, would be, say, in the first quadrant. So let's say we put it over here. I'll put my base here. So this is the base of the loaf of bread. I'm just going to try to straighten this out a little bit because I don't like the way it looks. It's very hard to write on glass and my pen slips. Okay. So, all right, we could put the base anywhere, but notice that I placed the base and now the slices are coming out of the base. So if you could just imagine these slices coming out of the base with each vertical cut that we make. They're coming out of the base. So in this little unit here, what we have is a very good description of what the base looks like. And that is usually two curves, the area between two curves, which we know how to find. But as we take a vertical rectangle that's perpendicular to the x-axis, depending on what shape is coming out of the x-axis, what the cross-section is, we have to represent the area of that cross-section in terms of the base, depending on what the x is. Whatever the x value is, we have to find the formula for the base. So the theme here is that if we call the area of this region here, the white part of the bread that's facing us, we call that A of x. We're going to sum up the areas of all of these cross sections from x equals a to x equals b. And when the number of cross sections increase without bound, then we have the definite integral. So to approximate the volume of this loaf of bread, we will sum up all the cross sections from x equals a to x equals b. And let's take a look at that on the next page. The areas of, so if the cross sections of an area of some geometric figure is taken perpendicular to an axis, and it must be perpendicular to either the x or y axis. If the cross sections are perpendicular to the x-axis, which is the most popular, then we integrate with respect to x, and the volume is the sum of the areas of all the cross sections from x equals a to x equals b in terms of x. But if the cross sections taken are perpendicular to the y-axis, then we integrate with respect to y, and the volume is the sum of the areas of all the cross sections expressed as a function of y from y equals c to y equals d. But now the question is, how do we get the area of such a cross-section? Well, it depends what that cross-section happens to be. The most popular cross-section is a square. And if we represent one side of the square as S, then the area of the cross-section is the area is just S squared. So that one is easy. All right, the next one is a semicircle. So, okay, so I should emphasize here that the base of the cross-section would be this green edge. The base of this cross-section would be this green edge. That's S as well. So if this is the vertical cut, this is S, then each of the radii are 1/2 S. So the area of the semicircle in terms of what we see in 2 dimensions would be the area is equal to 1/2, because it's half of a circle, pi r squared, which is 1/2 s squared. And we get here, when we simplify, we get pi over 8 s squared. This will be very, very important for us in a few minutes. The next popular one is the equilateral triangle. And I think this is the trickiest. How do we represent the area of an equilateral triangle if in terms of one of its sides? Well, if we drop the height here, okay, we know that the angles of an equilateral triangle are 60, so this would bisect the vertex angle. This would be 30 and 30. We have a 30-60 right triangle. Each of these sides would be a 1/2 s, because the angle bisector and the height are also the median. And the height would be also represented in terms of S. So we could have it as 1/2 the hypotenuse times the square root of 3. So this is 1/2 S times root 3. So the area of this equilateral right triangle would be 1/2 the base, which is S, times the height, which is 1/2 S root 3. So we could summarize that the area of an equilateral triangle in terms of one of its sides is simply root 3 over 4 times S squared. And that is also very popular. Another one that we see often is an isosceles right triangle with a base as a leg, and that one's really easy. The area of this triangle is 1/2 the product of its legs, which is 1/2 S squared. And then there's one other which happens once in a while on the AP. An isosceles right triangle with a hypotenuse on the base. Okay, so this one's interesting. This is the base. So now we have to think about how to represent the legs of this isosceles right triangle in terms of S. Well, that's just 1/2 the hypotenuse times the square root of 2. Let's not forget the square root of 2 there. So the area of this in terms of S would be 1/2 S root 2 times 1/2 S root 2 times a half, because it's 1/2 the product of the legs. And we get here S squared. Okay, now the 1/2 times 1/2 times 1/2 gives us an 1/8. But the root 2 times root 2 gives us 2. So the answer is just S squared over 4. All right. That would take care of those. So let's go back and review how to get the area between two curves. But this time, we're going to think of the area between these two curves as a base of a solid, of some solid formed by a geometric shape. So let's say we have f of y equal f of x and y equals g of x. F of x is in red and g of x is in blue. From x equals a, so let's say these are the intersection points, to x equals b. So to get the area bounded by these two curves, the area would simply be the definite integral from a to b of the top curve, which is the red one, minus the bottom curve, which is the blue one. And remember what this represents. It represents the height of any vertical rectangle at any given x by taking the distance from the red curve all the way down to the x-axis minus the blue curve to the x-axis. And when we subtract those two, we represent the height of the representative rectangle. Okay, now that is still the theme here. That's the only way to get the height of the rectangle, f minus g. That is a must, but I'm going to erase this now. Now, instead, let's say each cut or cross-section perpendicular to the x-axis is something. So that these are the vertical cuts. And these vertical cuts represent the side of the geometric figure. So this piece will be S, the side of the geometric figure that we were talking about, depending on what is on the base. So let's make a little list. Okay, so I listed all the cross sections we talked about. And remember that S represented the side of the square, S represented the diameter of the semicircle, S represented the side of the equilateral triangle, S represented the isosceles right triangle with the hypotenuse on the base, and then the isosceles right triangle with the leg on the base. And I tried to make 3D diagrams. Note that this is when the axis is rotated in 3 dimensions. So that's why the cuts don't look vertical. They look a little slanted because we rotated the x and y axes. But remember, the area of the cross-section for a square would be just S squared. But since S is top minus bottom, your integrand would look like this. F of x minus g of x squared, because this is S. For a semicircle, we had a pi over 8 on the outside, but here we had to square S. So it was f of x minus g of x squared. For an equilateral triangle, the formula was, I believe, the square root of 3 over 4 times S squared. For an isosceles right triangle with the hypotenuse on the base, we said that the formula would simply be would be 1/4 be the side squared. And then finally, if we have an isosceles right triangle with the base as a leg, it's simply 1/2 the side squared. But all of these would be integrals from x equals a to x equals b because the region is bounded by those two vertical lines. And these are the integrands right here. These are our integrands, everybody. And notice that with these integrands, there's something very special. It's top minus bottom squared. And we square the difference. Please do not get mixed up with the washer method, where in the washer we're required to square the f and g separately and then subtract. So it gets a little tricky here. So remember, semicircle is the one with a pi over 8. An equilateral triangle is the only one with the square root of 3 divided by 4. And we just have to remember which one's the quarter and which one's the half. The quarter is the one with the isosceles right triangle with the hypotenuse on the base, whereas the half is the isosceles right triangle with the leg on the base. Okay, so let's consider region R to be bounded by the graphs of y equals x squared and the line y equals 4. I picked two simple curves that are easy to sketch, and obviously our points of intersection here would be 2, 4 and negative 2, 4. All right, so let's try the following. All right, so let's set up an integral to find the area of this region R. And again, region R is this enclosed region here. This is region R. All right, so to get the area, we use vertical rectangles. And the formula would be the definite integral from x equals negative 2 to 2 of the top curve, y equals 4, minus the bottom curve, y equals x squared dx. Okay, that would get the area. If a solid S has a base of R, find the volume of solid S if each cross-section perpendicular to the x-axis is. So we're going to still use this vertical rectangle. And the limits of integration are still going to be negative 2 to 2 in every one of these. So if the cross-section's a square, we have the side squared, but the side is the length of the rectangle. So that's just 4 minus x squared squared dx. If each cross-section was a semicircle, then again, the area of the semicircle had a pi over 8 on the outside, but we have to square the side again. So it's top minus bottom squared. If we have an equilateral triangle, recall that the equilateral triangle had a square root of 3 over 4 on the outside, but the same integral, negative 2 to 2 of 4 minus x squared squared dx. If we have an isosceles right triangle with a hypotenuse on the base, then that area was 1/4 on the outside from negative 2 to 2 of top minus bottom squared dx. And finally, an isosceles right triangle with a leg on the base was just 1/2 from negative 2 to 2 of top minus bottom squared dx. So actually, these integrals are quite simple as long as you remember what coefficients go on the outside. And the fact that we have to square, it's top curve minus bottom curve squared, the whole thing squared. All right, let's take a look at the same example when we have to integrate with respect to y. So we're going to take the same region, region R, but we would like to set up an integral to find its area with respect to y. Well, for area, if we integrate with respect to y, we use a horizontal rectangle. And notice that we have to use y limits of integration. So the y limits of integration would be the two horizontal lines, y equals 0, which is the x-axis, to y equals 4. And the generic formula is right minus left. But we have to represent these as functions of y. So we have to now solve for y equals x squared in terms of x. But that's x equals positive or negative root y. So this branch is x equals positive root y, and this side is x equals negative root y. So our integrand would be the right minus the left dy. Okay, so that is how we would integrate to get the area in terms of y. Now, the reason why we did that is because I'd like to take a look at the solid S has a base of R, but this time we want to get the volume if each cross-section is perpendicular to the y-axis. So if each cross-section is perpendicular to the y-axis and the yellow region is the base, we have to integrate with respect to y. So all these definite integrals will be from 0 to 4. But again, the length of that green rectangle, wherever it may be, will always be right minus left. So all the integrands will be the same except we square. So for a square, it would be the integral from 0 to 4 of right minus left squared dy. For a semicircle, I just have a pi over 8 on the outside. For an equilateral triangle, I have the square root of 3 over 4 on the outside. And then finally, for an isosceles right triangle with the leg on the base, it's just a half on the outside. So if we know how to set up the area, we definitely know how to set up the volume of the solid, given that the area of the region is the base and we know the cross-section. All right, let's take a look at a GeoGebra simulation. So this is a GeoGebra program created by Steve Phelps, and it's a great visual on finding the volumes of solids with known cross-section. This green curve here is, say, f of x, and g of x is the red curve. And here's a slice perpendicular to the x-axis, okay? So I could move this slice over. Okay, now, I have cross-sections that are squares here, but we could have various choices just to give you an idea. And I could move this around, but so as I move this square, watch the 3D diagram where that square appears in the solid. Okay, so as I move it, we're slicing the solid so that each slice is a square. Okay, I don't know if you can see that square. There it is. So each side, each slice perpendicular to the x-axis is a square. So that's the square moving through the solid. So in 2 dimensions, we just see the base of the square. But in 3 dimensions, we could see the actual square coming out of the base. So the 2 functions that we graph are the base of the solid, and it depends what's coming out of the base. So if we look at the surface, that's something that looks like this. This is what the solid looks like. Again, if I move that square through it. You can see, I don't know how to describe this solid. It's almost like a hat where each slice is a square. Each square is different size depending on the length of the side, the vertical cut that you see in two dimensions. But that's our solid. Okay, and you see it from various angles here in 3D, which I really like. Okay, so notice what we're doing here. And the best part is that we don't even have to visualize it. Now with technology, we can have the visualization. So I think it's worth it. Now, suppose each cross section, instead of being a square, was a, let's see, lateral triangle. All right, let's look at that one. All right, now, so each cut perpendicular to the x-axis is a vertical rectangle, just like we're finding the area of curves. But now, this vertical slice represents the side of the equilateral triangle as it goes through the base. Okay, and if we look at it in 3D, see whichever way we turn it, we have an equilateral triangle. See, going through. And here we have an edge on top. See that the vertex of the isosceles triangles just map out an edge of the solid? That doesn't really matter to us. The surface of the solid, just out of curiosity, would look something like this. Okay, so it's a strange looking hat, but yeah, that's what it looks like. And it's solid, all solid in this case. Okay, now let's say we have the same two curves, and each vertical line segment is the diameter of a semicircle. Okay, so let's see what that looks like. So as I slice my base vertical to the perpendicular to the x-axis, I have a semicircle where that vertical line segment is the diameter of the base. So let's look at that at various angles. So look at that. This is beautiful. I love it. I wish I had this when I was taking calculus when I was your age. And the solid would look something like this. And that looks more like a, can't say it's a dome because the base of the dome is very strange, but certainly curved here. So that's what the solid looks like. And the last one I have here is, let's see, we have isosceles right triangles, and this can vary. Okay, here the isosceles right triangle, the leg is on the base. Okay, it could vary. The slice could be the hypotenuse. I've seen both renditions, but anyway, since we have this, I just wanted to show you what that would look like. So as we slide the isosceles triangle through there, notice that each vertical slice is the length of the leg of this isosceles right triangle, and that varies. We're going to sum up all those areas of those cross sections, and the surface looks something like, this also has an edge. Notice that black rim there? Okay, and that looks like this. Okay, so very, very interesting. Okay, there is another program that I wanted to show you next. And that takes care of our lesson on volumes by known cross sections. I've hoped you've enjoyed it. Have a great day.